going to talk about calorimetry, that is, measuring energy transfer. So first we'll start off with defining a couple of things for you. Something called the heat capacity, whose symbol is a capital C. What that is, it's the amount of energy that it takes to raise the temperature of an object by 1 degree Celsius. Now, every different object is going to have probably a different heat capacity. The thing about that is that we like to know these numbers, these heat capacities, but we'd have to have a table, infinitely long to put every object in there. On the other hand, specific heat capacity, symbol lowercase s, that's something that we can tabulate because that's defined as how much energy it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius. 1 gram. Now the units here for heat capacity are just joules over degree Celsius, or maybe calories over degree Celsius. And the formula that you use to calculate how much energy is transferred into or out of an object is equal to the Q, which is what that is equal to the heat capacity of that object times the change in temperature. Now look, the Q can be negative or positive. C is always positive. Heat capacity and specific heat capacity both always have to be positive. But delta T can be positive or negative. Remember, delta is final minus initial. So delta T is always final minus initial. That's a good thing to keep in mind. F is final, I is initial. And so if final temperature is lower than the initial temperature, delta T is negative, and vice versa if it's greater. Now, specific heat capacity, the units are going to be, most of the time you guys are going to see them, it's going to be in joules per gram degree Celsius, right here. Could be in joules per mole degree Celsius, that would be a molar heat capacity, or calories per gram degree Celsius, or calories per mole degree Celsius. But this, and once in a while this, are what you'll see. Now here, this is a really important equation, so make sure you guys memorize it. It's pretty easy. It's Q equals ms delta T. What it says is that the amount of energy that's transferred into or out of a substance is equal to the mass of that substance times the specific heat of that substance times the change in temperature. Again, final minus initial. By the way, notice the difference here. This is for a specific object heat capacity is. Specific heat capacity is for a substance, gold, carbon, water. And it doesn't matter how much you have because it's always for 1 gram of that. That's why we can tabulate it more easily. So memorize these equations. Oh, and the specific heat capacity of water is 4.184 joules per gram degree Celsius. You should memorize this. This is actually at 25 Celsius, but close enough. Now, when we perform an experiment at constant pressure, remember Q, this is what we're talking about here, thermal energy is equal to Q sub P, and remember that's equal to the change in enthalpy for that process. Now what we're using here in this calorimetry is the first law of thermodynamics, that energy can be neither created nor destroyed. In other words, there's two basic scenarios here. First scenario over here, we take something hot and we add it to something cold, or vice versa. So let's say we have a lump of gold that's really hot, and we put it into a cup of water, a calorimeter, coffee cup calorimeter, that has some cold water in it. Well, what's going to happen is the gold metal is going to get cooler and the cold water is going to get warmer. That's what this says here. What this says specifically is that the amount of thermal energy that goes into the cold water is equal to the amount of thermal energy that comes out of the hot gold. So this negative means it's coming out. We also do experiments where we do a chemical reaction in a calorimeter. Here the system would be the chemical reaction and the surroundings would be the water in the cup and everything there. So here if it's an exothermic reaction, it releases heat, then the water, the solution would get warmer. And what we do is we can weigh the solution, get the mass, we know the specific heat. If it's water, it's usually 4.184, and we can measure the change in temperature with a thermometer, the temperature before and the temperature afterwards, and we can get how much thermal energy went into this solution. Now we know how much thermal energy came out of the chemical reaction, and you'll see an example we do that illustrates that. So when it's the first scenario where you're putting something cold or into something hot or something hot into something cold, sometimes, not all the time, you're asked to find what the predicted final temperature of that system would be. And so what we do here is, remember, Q is mass times specific heat times delta T. We write that out specifically for the cold substance. Mass of the cold, C stands for cold, H stands for hot. Mass of the cold times specific heat of the cold times delta T, T final minus T initial of the cold, is equal to negative. Watch your signs here. It'll really mess you up if you don't do your signs properly. Mass of the hot times specific heat of hot times delta T of the hot. Notice that I have differentiated the initial temperature of the hot and the initial temperature of the cold because they're different. But they're both going to come to the same final temperature, and so I didn't differentiate there. These numbers are the same, which is why when we rearrange it, we can solve for final temperature and get this. I'm not saying memorize this. You can do the algebra yourself, but it's just a useful form. So let's do an example. We want to calculate the final temperature of the system when this much gold at that temperature is added to that much water at that temperature. And we're going to assume that we have a perfect insulator. No thermal energy is lost to the surroundings. That's almost never the case, but we're not going to worry about it here. In other words, all of the thermal energy that comes out of the gold goes into raising the temperature of the water. That way we can say negative Q of the gold is equal to Q of the water. So, and that's the specific heat of gold, 0.1291 joules per gram degree Celsius. So we're going to plug into our equation there, and pulling out of this problem here, we see that the mass of the hot object, the gold, is 43.12 grams, its initial temperature is 92.22 degrees Celsius, and its specific heat capacity is 0.1291 joules per gram degree Celsius. And the mass of the cold object, which is the water, 150 grams, initial temperature 22.91 degrees Celsius. And notice, okay, watch out for this. I did not give you the specific heat capacity of water in the problem, and I probably won't on homework and exams, because that's the one and the only specific heat capacity that I will ask you to memorize. So it's 4.184. Anyway, we're going to plug into the equation. So this is that equation, the rearranged form of the Q cold equals minus Q hot, where Q is ms delta T. Plugging in for the mass of the hot, specific heat of the hot, initial temperature of the hot, plus mass of the cold times specific heat of the cold times initial temperature of the cold, divided by mass of the hot, specific heat of the hot, plus mass of the cold, specific heat of the cold. Now I'm going to look at sig figs with you guys real quickly here. When we're going to follow the order of operations, keeping track of sig figs at each step. Multiplying out all the parentheses here, this one gives us to 4 sig figs, 552.3 joules. Notice how the units cancel. Grams cancel, degrees Celsius cancel. We're left with joules here. Over here, same thing. 4 sig figs, we're left with 14,370, and then sub 8.3 joules. On the bottom, the grams cancel, but that's all. We get joules over degrees Celsius. 4 sig figs, we get 5.566 sub 7 joules degrees Celsius. And here, this gives us 627.6. Only, that should be 4 sig figs. And then when we do the addition on top and bottom, we get these two numbers. Notice how the units cancel. Joules over degrees Celsius gives us degrees Celsius. And we end up with 23.58 degrees Celsius. Let me fix that. And there you go. So, and that is the final temperature of the system. Now, when you're doing this kind of calculation, you should always check and make sure it makes sense, right? You know that when you take something hot and something cold and put them together, the final temperature should be somewhere between the two, right? So somewhere between 22.91 and 99.22, and yeah, it is. Notice it's a lot closer to the temperature of the water than it is the initial temperature of the metal. That's primarily due to the high heat capacity, specific heat capacity of water, plus there was more water in terms of mass than there was gold. All right, here's the other scenario where we do a chemical reaction in a calorimeter. Here it's a coffee cup calorimeter, and we want to find out the the delta H, the heat of reaction. So this reaction here is hydrochloric acid and sodium hydroxide making sodium chloride in water. The way I have this problem set up is we have the same number of moles of acid and base. That way we don't have to worry about other stuff. The idea is that the thermal energy that comes out of the reaction goes into raising the temperature of the solution. It's an exothermic reaction, and you know this because the final temperature is higher than the initial temperature. The Q of solution is mass times specific heat times delta T of solution. Now I've given you a different specific heat of solution because this actual solution isn't just water anymore. Now it's a solution of sodium chloride, and that changes its specific heat capacity. So there it is. So what we're going to do is find the Q of solution right here, and it's 471.6 joules, and that's equal to negative Q of reaction. So we get the Q of reaction is negative 471.6 joules. Converting that to kilojoules, we get negative 0.471 sub 6 kilojoules. Now, the problem asks for the delta H of reaction in kilojoules per mole. So per mole of sodium hydroxide or per mole of hydrochloric acid, it doesn't matter because we have the same amounts and the stoichiometry is 1-to-1, which we'll see in another chapter. So all you do is you take the amount of energy that came out of the reaction and divide by the moles of the reactant, and that gives us the delta H, or the heat of reaction. And that is our delta H of reaction, negative 59 kilojoules per mole. Next. Now, that was all at constant volume. If the volume's not that was at constant pressure. If the pressure is not constant, but the volume is, we have what's called bomb calorimetry. And this is a little more complicated setup because in here we have to make sure that when we react something, that if it gives off a lot of energy, that it stays contained and the volume doesn't change. This part is called the bomb. The basic setup here is we have a big tub of water, something to stir it. We have a thermometer, of course, in it. Nowadays they'll be digital. We also have this bomb part in here. This is probably a stainless steel container with a screw-on lid that has an inlet for oxygen and also an outlet, which isn't shown here. What you do is you take your sample. What you do is you're gonna combust or react with oxygen, some compound. What you do is you weigh it out, then put it into this cup in here, tighten the lid, then purge it. That means push all the air out and fill it with oxygen to a high pressure. And what that does is that just makes sure that the reaction goes to completion. And then you press this button. Unfortunately, you don't see any bangs or hear any bangs or see any flashes. It just kind of goes. But what happens is inside of here, that ignites this sample, reacts with the oxygen in here, and releases thermal energy, which heats up the bomb, the water, and everything else around it. And this thermometer here, this measures the rise in temperature. It gives us our delta T of the water. So the Q of the bomb, which is basically the water here, is going to be the mass times specific heat times delta T of the water. So if you weighed this before, you know how much the water weighs. You know specific heat, 4.184, measure its rise in temperature. You know how much thermal energy went into the bomb, the water. That's how much energy came out of the reaction, and you can do like we just did before. Notice that in this case, what you're really measuring is the change in internal energy, whereas when we did the coffee cup calorimetry, the constant pressure calorimetry, we were measuring the change in enthalpy.